Morning, folks. I think we're supposed to have 25 of you this morning, which is better than we normally have, better than the other sections I had. Um, but can someone confirm you're actually out there and that you can hear me and you can see my screen? Good. Morning, everyone. Okay, so let's get underway then. Um, that last class, okay, always started with a couple of pictures. Last class, I showed you what was called Hell's Point, point of land that um, there were waves crashing over in the distance because the remnants of a hurricane that was passing by. And we had lots of waves, but we didn't have stormy weather. Yesterday morning, all that's passed. And so it's nice and calm out there first thing yesterday morning. It was really nice. Um, that it was just absolutely quiet. There was no wind at all. And normally you can hear waves rolling on the beach or crashing against rocks below us, that sort of thing. Couldn't even hear that. All I heard were a few birds, a few squirrels, um, and it was really quite nice. So uh, just a few more shots for you. A different one than I gave yesterday's class. This is this morning, and it was again really quiet and calm. And looking from a different perspective, that's not the ocean. It's a pond that's just behind the ocean. You can see lots of barns, and so this area, I know you may think of Lunenburg as all fishermen. But a substantial number of people in this community, 50 years ago anyway, were they were still farming, and still lots of fields that they farmed previously. I think grazing cattle, dairy, that type of thing was probably predominant. And now the deer we see grazing. This morning we saw two groups, one about, I don't know, there may have been 10, another of 6 or 8 that grazing in different spots. And so it's um, where I am, it's all rocky and that sort of thing. But there's land that's well, a little ways away from us. If you know the beaches of Nova Scotia, uh, this is over in the next bay on the other side of the hill, that Heartland Bay. And if you've ever heard of Hurdles Beach and you're a surfer, Hurdles is a very popular spot for sort of like Lawrencetown Beach is in Dartmouth, popular among surfers. And this is looking at it from a very different perspective than the beach. It's the beach most people go to is way over here, accessed by a different road. This is a little beach that most people don't know about. That's all still part of the same bay. But in between, there's this huge hill. And you can see this house up here at the top of the hill. That that edge along there, that's not rock below. That's all really nice, rich soil. And so that's farming took place over on the other side of the hill. And 50 years ago, took place on this side of the hill. I'm told that my wife's ancestors owned some property along oceanfront. It's all underwater. It's all in the air. Every year, this edge falls backwards and it creeps in, and it's all falling into the ocean because there's nothing to hold it there. And that house eventually, in another 40 years or so, will fall over the edge and into the ocean. It was sold a few years back for about $700,000. Crazy people that bought it. They're Americans. What can I say? Anyway, last day with both classes. Um, yeah, yeah, it's been Gaff Point. Um, Gaff Point is way out here on the left. So if you go out Hurdles, if you go out, there's a road that takes you out here to Hurdles Beach. Used to be a nice canteen out there called Gladys Canteen. It's really good food. Um, and that if you go out further, it's Gaff Point, which goes way out there. It's a good hiking spot and that sort of thing. And again, it's a really nice spot. The land back here didn't used to be worth very much, and I understand that um, some relatives sold off many years back a large portion of Gaff Point for a new kitchen refrigerator and a new stove. Um, the land was worthless. Nobody cared about it. Nobody came out here. It was all pretty wild and rugged, and teenagers came out here to party, but that was about it. Anyway, uh, off we go. Um, so, oh, that's where I wanted to go. The last few days, so all through the weekend, getting a lot of emails about, or at the beginning of the week, about assignment three. People had been starting in on it, and many getting stuck right at the very start. And it's just, they got very, very discouraged. Like, how am I going to get through this if I can't do 1A? And so I asked the class, my first class yesterday, you got any questions about it? And it was just a, if you could talk, not just chat. It was yes, 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 yes. So that's what I'm going to do. I'm going to spend, with those classes, I spent 45 minutes going through questions one and two on the assignment. And I think once they saw how those things were doing and the different things of how to do a chart, how to find the residuals, how to find the correlations, how to find the equation of the line, and they felt, okay, now I understand what's going on. And I know the assignment's worth a lot of points, so it's important you do well on them. But it's also the assignments are when you actually apply this stuff. And in my mind, the assignments are always an important part of the learning process. I don't necessarily use them for testing. Um, and if we were in a face-to-face class, then I'm used to having Wednesday and Thursday classes being taken up at least half the class with questions about the assignment that's due Friday. So that's what I'm going to do with you. So I'm going to take this data. I've got a bunch of junk in here. I'm going to delete so that we do it all from scratch again. That this is leftovers from yesterday. So bear with me as I delete all this. But okay, I think that's it. So this is the, uh, okay, fine. I got some problems with formulas, whatever. So this was the data you start with, and it's the pre-crisis data. And if I go and look at the assignment questions, let me zip up to the top. Hopefully you can see all this. If you aren't seeing all of my screen, please let me know that you should be seeing right now the assignment questions. I'll make them even a little bigger. And so it starts out, we're going to look at the pre-crisis data. So we're not going to look at the tab with the post-crisis. That it's a reasonably large data set, almost 2,000 records here. And that I went and looked at the average prices. That was $116, which you won't find anything in Halifax for that. You won't find anything in Nova Scotia for that. The assessment is an assessment is what the city, town, whatever thinks the property is worth, and they use it as a basis of taxation. And so cities and towns get all of their income for the most part from property taxes based upon these assessments. So they want to have good estimates of it. As a homeowner, you don't want your assessment to be too high because it means you pay more tax. So um, homeowners will try to convince the city that, oh, no, 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 my house isn't worth that much. Your assessment's too high. And on the other hand, the city would like the assessments to be as high as possible because it allows them to tax more. In the US, where this data comes from, not only do the cities get most of their income from taxes, property taxes, but I think most of the states get their income from property taxes. So it's a big deal. People are concerned about how accurate assessments are. So what we're going to do to start out with is to see, do assessments accurately reflect selling prices. And on average, they're close. It's only about a 1 or 2% gap. But so I've asked you to do a screenshot of take a picture of assessment on the horizontal, left, right, and price on the vertical. So let's go. I'll go back to my data. So with this one, I want price data and assessment data. So let me just grab a couple of columns, and I recommend to you to just go in each question you do, create a new sheet, like a new piece of paper you're working on to answer a question, and uh, just include the data you need for your question. So I don't need this stuff, so I'm going to throw that out. And I'm going to give it a name because I'm going to create a lot of sheets and I don't want to forget which is which. So this is my question one sheet. So if I was to go and take these two guys and insert a chart, and it suggests a scatter chart, good, that's what I want. Great. So is this it? Not quite. I know the numbers look the same here and here because the assessments and prices are close, but actually it's gone and drawn the assessment on the vertical axis. I want it on the horizontal. I want assessment here, price there. And so usually my clue is that if I go and just throw a chart like this together, it'll often put what's a label to a title on my chart that reflects what's on the vertical axis that's over here. So this is the wrong one. What some students are doing is saying, well, I just want to switch it then. Just switch the axes. And so switch X and Y around. That's not a big deal. Here's a button that says switch row and column. That sounds like it, doesn't it? And I get an error. What's wrong? Well, my data is in columns. It's not in rows. That's like it's like it would treat all of these as as variables with one observation for each one. So no, this isn't the way my data is. I want to switch the axes, not the rows. There must be a simple way to do this in Excel, but I've never figured it out. So what I do is I take the price column and I cut it and I move it over here. Okay. And now I've got assessment on the left, price on the right. That's what Excel wants. It wants the first column to be X, the second column to be Y. Then if I take the two columns, I go and I insert chart. Looks almost the same. Doesn't it look almost the same? Yeah. Very little difference, but it says price up here. And actually, this is the correct chart. This is the wrong one. It's hard to tell the difference between them. They look very, very similar to each other. But this is the right one. That's the wrong one. There's question one. Let's go back here and see what also, well, that's 1A. It then asks me what's the correlation between these two. So that I need to go and use my function for correlation. Where is that? Back here again. So let me get rid of the chart I don't want. And I should remind you, I want you to label these. So you should go and add chart elements. So I want on the horizontal, I want it to say assessment. And, oops, wrong one. On, this is axis labels on the vertical, I want it to say price. If you don't like it that way, I don't. I just have trouble reading. I can go and format these things and change it to horizontal, but you don't have to do that. Okay, so I got a nice little graph here. The then it asks you to find the correlation between these two. So that correlation is one of the data analysis functions. So we look to data to find that. It's our tab. We We go to data, we go to data analysis, we look for correlation, and it's got a bunch of things in here. Let me just take that out. So where are my variables? My variables are in column B, starting at row 1, and they are in column C, and they go down to 1978. In columns, I have labels in the first row. I put my labels in, and I'm going to put it on my chart here. I'm going to put this just below my picture. So that's, let's put it in E16. I'm trying to keep it all together because this is just all question 1 stuff. Here it is. So it gives it to me. You can see, I hope, down here at the bottom that the correlation is 0.94466. So it's a fairly high value. That correlations, the biggest you can get is 1. And that means that there's a perfect straight line. There's no variation at all. And correlation of 0 is when there's nothing. It's just like a shotgun blast. It's no pattern at all. And so on this scale between absolutely nothing and a perfect line, we're pretty close to the perfect line. And that looks like a very strong pattern there. So yes, assessment seems to be related to what the price is. And probably a decent predictor. So we could use the regression function to go and try to build a way of predicting from that. Yeah, it's being recorded. And I'll post it immediately after. I've also posted the video from yesterday at 11:30, and then there was problems recording the one at 1 o'clock, but it's posted there in a top hat recording. It's not as good, I find, but yeah, and we're going to do this on assignments 4 and 5. I think I'm going to try to set up my class so that the class before your next 2 assignments are due, we'll go and talk about the assignment, because I really don't care about the grade you get. I'm more concerned about you understanding it. Okay. So it asks for you to fit the line. Okay. If you look at this, we can imagine a line that's going through here, and I can find the equation of it again through the data analysis tools. That if I go down here to regression, this is what we've been doing, and right now this is a simple regression. We just have 1 x variable, 1 y variable. So my y variable is in column C, that's right, but my x variable is in column B. See that? So y is what we're predicting, the vertical. X is what's on the left or right. It's what we're using to predict. And just have to give it the location of those. I've got labels again. This time I'm going to put my output over further to the left here. Let me put it in column H. And not 1. I'm going to put it down about 16 as well. And I'm going to ask for the residuals. Not that I need them at this stage, but I like to get in the habit of always remembering to do it so that I don't have to go back and get them again afterwards. And so let's go. You've got all that in. Good. There, I've got my output. If I lose you along the way in talking about these things, that stop me before I go too far, because you may pick it up when you go back and watch the video again or check the slides. But this isn't in the slides. It's only in the video. It's your only recording of what we're doing here. So here's my model. And I like to look at this one first, just to give me a sense of how did I do. And I only look at 2 numbers. I look at R-square and I look at standard error. Okay? That the R-square says I explained 89% of the variation. I don't know what that means. I should know. I know how to measure it. I know all the theory behind it, but I just don't like the explanation. But I do know that the closer it is to 100%, the better my model is. And so this is close, just like your correlation was close to 1. My R square is close to 1, so that's good news. My standard error isn't as great news. It says that if I was to predict the price of a house based upon its assessment, so if I was told the assessment is $150,000, what do you think the house will sell for? And I come up with a prediction for that. I wouldn't be surprised if my prediction was either too high or too low by at least $17,000. Maybe even twice that, could be $35,000 off. That's a huge amount of money. Um, that I'd kick myself if I guessed that far off in terms of my house price. Um, that anyway, that's what that thing represents. So what is this model that I've got? That I have to go down to this table and look at coefficients. And I've got, this is a straight line. A straight line has an intercept and it has a slope and it has an x variable. So my equation here would be, let me just write it out. Okay. It would be that my estimate, because it is just an estimate, it's not perfect. So I know there's good, but it's not just an estimate of one house, it's an estimate of the average. So the average house price that I'm predicting, not the assessment. I'm using the assessment to predict price. I start out as it's being $8,174, plus I'm just ignoring the decimals. I should include those, but now. And then for assessment, total assessment, its correlate or coefficient is this 0.9395. 939, oops, 95. And I just multiply that by total assessment. And that is the equation that I'm getting out. And if I was to fit a line, I'll just show you again what I mean by that. If you take this, again, something you don't need to do, but you may want to, if you have time, and I know you're pressed for time, you've got lots of things you're dealing with, but if you do get time to explore things while you're doing assignments, and hopefully it doesn't mess up your assignment, should you include decimals in your assignment? I would round off my numbers. These are big numbers. I'd round off my decimals usually to 2, like that. If I was doing this, honestly, where did I write that line? I would have rounded this to 0.94, and I would have rounded this to 8,175, because I'd round this guy up. And I don't think it's appropriate really to show too much detail, because, as I said, these are only estimates. And so suppose my answer is wrong by $30. I already said my forecasts are wrong by $17,000 a lot of the time. Being wrong by 30 or 100 or 500, who cares? Okay, it's don't. If you give too many digits, people think the number is more accurate than it is. In fact, a lot of the numbers we work with are just ballparks. They're not accurate. So, when I hear polls, when it says more than 42.6% of people think more than, yeah, it's because it was 42.64 or something, okay? That's where the more comes from. But who knows the difference between 42.6% and 40%? That I might say over 40%, because we think in big chunks, big numbers. That it's, I hate it when people, by saying 42.6, they think they can measure things that precisely, and we can't. We never can. Anyway, back to this thing. So one of the things you might want to explore sometime is you can change the layout. It's the same chart, but the way it's laid out. And you see a whole bunch of little boxes here. One over here that puts um, uh, stuff to the right, and it may tell you some of the things it puts in. I like this one here. Whoop, oh, where'd it go? Where it puts a line in for me. Or this one here that puts a line in and actually gives me the equation. Let me take this guy. I know it may be hard to see. And I'm going to take this and move it over here. I'll make it bigger so you can see it, see this portion of it. That was the equation of my line. Okay. This was the intercept. This was the slope. That's my x variable. Okay, I wrote it in a different sequence with the intercept first and the other stuff second. But Excel can tell you what that line is. And let me just go back over here to, I want to play with this guy. Format it. Okay. I guess. And I just want to take, it's not going to let me do it. Let me do something else then. I just want to be able to show you what's happening with this line. And I just want it to be longer. And I'll make it bigger. Okay, so this is the line that goes through the scatter, and that's the equation I've done. And as you can see, sometimes my prediction is too low, and sometimes it's too high. And it goes down here. It doesn't quite hit 0. It's crossing down here at 8,000. That's where my intercept is. And the slope is how quickly that line is going up. So that's the equation of the line. I could go and find out the price of different homes. I could go down here. Here was my formula. So let's suppose I've got a house that's got an assessment of 150,000. Okay. Then I could work out what the price is by saying, well, it's equal to the intercept plus I, that's my slope, times assessment, 150,000. What do I get? Oh, that's pretty close. It's a little bit high. It says the estimated selling price will be 149,000. Pretty darn close. So that's all there is involved in being able to actually use this formula. So you can build it in there. You can pick different values for here. And if I wanted a $300,000 house, it's 290,000. So a little bit too high. If I had a $100,000 house, whoops. Okay, it thinks it'll sell for 102,000. And so you're asked to look at a $50,000 house and a $200,000 house. What would the price look like? So it's the next one I've got here. I want you to go and try to explain what the slope and the intercept means. Take your best shot at it. It's sort of like getting into causal analysis. It's not that the assessment causes the price to go up and down, but you can talk about the relationship between the assessment and the price. And standard error, as I mentioned to you before, gives me an idea of how far off my predictions are going to be. Then I asked you to go and look at a whole bunch of variables. So let's go and jump into question 2. Where am I? Housing bubble. So let me get my data again. I'm going to grab it all of it. I'm not sure what it is that I need to save. And I'll start a new sheet again. And I need acres, above space, basement, deck. I don't need baths. Don't need toilets, fireplaces, beds, rooms, air conditioning. But I want age, so I'll get rid of these. Let me delete them. I want car, but I don't care about condition. Get rid of them. And I don't need any assessment stuff. So this is the only data I need. So again, I'm just trying to keep my workspace clean and organized. There's no junk on it. Mind you, if you saw the little table that I'm working at the moment, it's covered in junk. That's where my desk would normally look at work. But get all the other stuff out of the way. You might want to look at the data a little bit. Interesting, a whole bunch of zeros here. A lot of zeros there. Most people have decks, or a lot of people do. They don't have basements, and they don't have garages. Yeah, that's common. A lot of places don't have garages. In Canada, basements are more common. Um, that if you don't have one, it's probably then it's been uh, built with a crawl space underneath, or it's built on a slab. That the Looking at numbers look pretty small for space, but you can look at that. So those are the variables I've got, and it asks me to do what with them? It says find the correlations of the explanatory variables, those are my x variables, with price. So I'm going to do it with everything. So I want to know how acres, the size of the building lot, is related to price, how the living space is related to price, the basement's related to price, and so on. And those are correlations. So I go to data, data analysis, go up to correlation. Okay. Okay, where's my data? Well, my data is from column A and row 1 all the way over to column G and row 1978. They're arranged in columns. I've got labels. I want to put them on the same sheet. I'm going to put them over in uh, H1. Again, although normally I've advised you when you're doing a project, you may have your data in one place and then you have a new sheet each time you're doing stuff. If I'm doing little things like this at a time, I like to try to keep my output with the data I use to generate that output. So I'd like to keep them in the same place. And maybe I'll repeat this a few times over, but I want to make sure this is the correlation that goes with this data set. And so this is the sort of table you're going to get. And in this case, we're looking at price. So we'll look at those numbers. If price happened to be, if I was looking at basement, then I would be looking at these guys, this, and whoops, and the ones down below it, okay, the things in its row or its column. But right now, this is one of the last guys, and so it's going to be just this bottom row. And the rest of the numbers I don't have to look at yet, but I may want to look back at them later. They'll tell me how the size of the deck is related to the size of the house, or to the age of the house, or to the size of the garage, something like that. So with price, it says it's positive, saying a bigger piece of property helps increase the price. It says a bigger house above space. This is living space. Its correlation is fairly high with price. Size of the basement. Yeah, you got a basement, that'll drive up the price. You have a deck, that's going to increase price. If it's an old house, it's going to drive down your price. Old houses need repairs. And if you've got a garage, that's going to drive up the price. So these are the correlations. Generally, if I'm looking at what's the strongest one, I don't care if it's positive or negative, so I wouldn't pay attention to the negative, but I want the biggest number, and that's this one. And so the next thing I ask you to do is do a scatter chart of above space and price. So take above space and price and insert chart, and it says put in a scatter chart. Let me move it over here. And I should label it. I should say this is above space here. This is price up here. Above space or living space would be a better name. And here I've got price. And I may want to flip that around. I do seem to have a somewhat strong pattern. I've got a bunch of odd ones way out here, but even if I ignore those ones way over there, this group, this blob, does seem to be sloping uphill. These guys are, in a sense, outliers. They're not like all the others. That in terms of the size of the homes, those of you looking, if you're in a 2-bedroom apartment, I bet you've got 900 square feet, 800 square feet anyway in it. That's a lot of apartments do. This is a house, and it looks like some of them are as small as about 400 or 500 square feet. Even a bachelor apartment is probably bigger than that. This is really, really, really tiny. A small house tends to be like 1,200 to maybe 1,400 square feet. I have a fairly small house. My cottage is down here at 800 or 900 square feet. So we've got a modest number of fairly large homes, and we've got some that are super big. That's really, really big. What do you do with all that space? Okay, what do we have to do next with it? Oh, it says, would I have confidence making fit the regression and find the equation of the regression line? Okay, so we did that before. Different data set though. So I could go up to data analysis. I want to do regression. Okay. So my X variable, I've got to find where have I put price. Hold on here. I have to go over. Second, maybe I have to go here. Highlight this stuff. There we go. So price is in column G. So from G1, G19, 78. And above space is over there in column B. Oh, good. It's already marked column B. I've got labels. I want to have some output. I want to put it below my picture. I'm going to probably put that down, and let's say it's H24. Check off these boxes down here, residuals, residual plots, because we will have to use it in this problem. Use it a little bit later. So it's hopefully done something way down here. There it is. So what's our model like? Is it any good? Look at the R-square, 0.5. It's actually in practice pretty common to get an R-square that's 0.5 or much smaller than that. It's hard to make accurate predictions. It's hard to get a great model. The standard error, it says if I'm just predicting house price using this, just the floor space, don't be surprised if your predictions are wrong by $37,000 or even more. Maybe it's even $70,000. And if you looked at your graph, and if I had, just to give you an idea of what we're looking at here, let me go and do that quick layout thing. Get that out of there. I want some space here. And draw my own line here. Oops. Hey. It doesn't seem to want to let me do this. Here we go. I just want to try to draw a line right on top of the old one so that we can see it better. These little dotted line I have trouble seeing. Make it bright, make it fat. There, now I can see it. Okay, so, and I can use that later. So yeah, it says start at about 13,000 and then go up. But notice how big the spread is above and below that line. It's a, 150,000 or 1,500 square feet. Has a price between zero, that's what it seems to suggest, and $300,000. That's quite a big range. Okay, back to our output here. That this is the interesting stuff. So this is my estimate of the average price. So this is the estimate of the line on there, not the little blue dots, but the orange line is going to be $13,311 plus $88.65 times the amount of space. What does that formula mean? It says that this slope that's here says that if I make my house just a little bit bigger, 1 more square foot, its average price will go up by $88.65. And if I demolish my house, so there's no space, then I can expect that the land will sell for $13,311 on average. Not that we've got any experience in that, because with this graph, we don't have any houses that are down here. But it's just if I extended that line all the way back, it would hit 13,000. That's what your intercept is. So that's the equation of my line. Now let me rename this to question 2. And let me go back to my questions. Okay, so I built a model. I've given you some idea of what it is. And now I'd like to go and look at adding another variable. And to do that, what I was suggesting to you last class and the class before is to look at your residuals. So let's go back here. And as I said, my predictions would be wrong. I'm high or low in my prediction. And that's what a residual is. So for the first house, it predicted a price of $74,919, and the actual selling price was $74,818. Very, very close. That it was only off by $101. Okay, my guess was $101 too high. With this one, my estimate was 100. Whoops, excuse me. Didn't mean to do that. With the second one, I predicted it would sell for $106. That ended up being $30,000 too low. It actually sold for, I presume, 140 or 136,000 or $137,000. Sold for a lot more. And so these are my residuals. These are the mistakes I've made. And what I want you to do is copy the whole bunch. You only really need the last column, but let's just take all this stuff because we're going to go and we have to work with it. And so I think I'd rather just start with a clean sheet. So we've already got a lot on this one. So it's into a new sheet. And I'm going to need some data on the other variables. So what have I got here? I don't need price, but I do need these other x variables. I don't need price because I'm not going to predict price now at the moment. Well, maybe I will need it eventually. Let me take it anyway. I probably will need to use it. I'm not sure if I can use it this way, but where am I here? So I can throw it in. What I want to do is look at the residuals and see how they're related to acres, above space, basement, deck, age, car, not price. So to do correlation, I look to data, data analysis, find correlation in here. There it is. Okay, where is my data? My data starts in column C and row 1, goes all the way across to column I. I'm not including price, okay? Because I'm not looking at correlation with price. I really should delete column E, but I'm going to leave it in just to show you something. Normally we would delete it because we've already taken account of the amount of space you have. So let's see what I get. Here's my table and make it big so you can see it. So this time I'm interested in predicting the residuals. And so I'm going to look at this column. Last time it was all the stuff I wanted was in a row. And the diagonal is always ones. And these are the correlations between each of these variables and the mistakes I made. That so it says if the land is big, I'm going to make a bigger mistake. It's correlated to 0.2. Let me skip above space. Basement, same thing. Bigger basements, bigger mistake. Deck, bigger mistake. Generally, that the price turns out to be higher. Age, on the other hand, is negative. That doesn't mean it's a smaller mistake. It means that the error that I make goes in the other direction. That old houses I'll probably overestimate the price for. And those with a big garage, I'm probably going to underestimate the price. So I've got correlations with them. What's this one here? And if you're not familiar with an E and a number, that's an exponent. When it says E minus 15, it's like taking this number and moving the decimal place over 15 places. That would be a number like 0.123. I don't know if you can see that. It's a really, really tiny number. And again, it just goes and writes it that way. Let me make it column wide. Oh, it still doesn't want to. Let me just, can I get it to show? Whoops, wrong way. Let me get it, force it to show all the decimals. Will it eventually do it? No, it doesn't. Oh, there it goes. Maybe. Now it still wants to put it in scientific notation. Oh, well. It's a super small number. It's, from a practical standpoint, it's 0. Okay? And so my mistakes and the amount of floor space it is, they're not related to each other. And they shouldn't be because I've already taken account of space. So these are my best guesses knowing what space is. So I shouldn't have an error left over that has to do with space. So that's why normally I wouldn't even bother having it in here. Okay. So these are the ones I've got to work with. I want the one with the strongest correlation, and it's the one with the biggest number, even if it's negative. So look at absolute value, and that's age. And then I tell you, go and redo this problem of predicting things using above space and age. So, so this I think was 2F. I think that was it. Where's the question? So, boom, 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 boom. Should find that age, okay, is the strongest correlation. So I'm going to redo this and look at my new model. So I'm going to redo it. I'm going to go and I want to use this, and put in my new sheet, and I want to use age, and I want to use to predict price. And we'll make it big so you can see me, or see the data. You can already see me. And now fit a new model. I want correlation to fit the model. That's regression. So correlation is figuring out strength of relationship when you're being asked for a model or finding a line. That's regression. My y variable is in column C. And my x variables are in columns A and B. Both of those columns. Labels, output, I could put that in E1. And I want all the residual stuff. Just out of habit, I'll ask for it. And so here's my output. Okay, so how do we do? So before R squared was 0.5, now it's 0.63. That's better. It's going in the right direction. Still not 100%. Standard error was 37,000, now it's 32,000. That's a bit of a disappointment. It's better, but it's still a lot of room for improvement. It's not great, is it? We skip this middle table. So what's the equation? My new equation is my estimated average price is $60,000. Oh, 9 plus. Now space before was worth $88 a square foot. Now it's down to 85. Times space and age. Oh, its coefficient is a negative, minus 696.65 times age. That's the equation of my line. And so if you told me you have a house that's 2,000 square feet and it's 40 years old, I'd put in 2,000 here and 40 there, crunch the numbers, and I get my estimate. And you'll notice age is negative. And I asked you about that. Why? Okay, I think I asked you about that. In question 3, I think I asked you about it. Question 3, same idea, but what we're going to do is put all the variables in there, not just 2, and see how much better we can get with all of those variables in there. And so, and again, I should probably be renaming what that tab is so I remember what I've studied here. And that's what I've covered with the other 2 classes. It took longer with you. I'm always taking longer with you, I think. But anyway, any big burning questions about the assignment? I think you can do 3 now that you've seen all of these steps. We've done most of them, plots, correlation, models, twice at least. So I hope you're going to be comfortable at this stage. Are you sort of good? Any questions? Nobody's typing? I can jump ahead. Feel free to pose your question as I move ahead. Quick review of where we are. I've talked about this 3 times over now. Just takes a long while for it to sink in. I think with a lot of this stuff, people don't get the first time or the second time, and many times don't get it the 3rd or 4th time. But we'll keep trying. So we've moved to modeling, and we started out looking at value estimation and using regression to do value estimation and at the same time do causal analysis. And I just did causal analysis. I had numbers in my formula that said how much the value of a house would increase if I made it bigger. So if there's more space, it has more value. So I think there's a causal relationship between that. People pay more for bigger homes. But yeah, how much more? $88 per square foot or $85 if I'm taking into account age. And you can see later when you put in the other variables, after you adjust for those ones, what do you think the value is? So it's of that variable, assuming everything else stays the same. I was going to do a discussion, but I skipped it. I wanted to know, can you think of other ways of doing value estimation that aren't regression? And I'll just throw one quickly at you. One sort of I used a few years ago, not necessarily for value estimation. Oh, come on. It's not going to let me move on. Okay. We had this problem before at last class, didn't we? So let's, oh, Dora's playing with her toys. Okay. Do. Oh, somehow I missed that slide or didn't seem to be there. Um, so um, we can use other strategies to do value estimation. Um, that if, oops, let me make this smaller so I can see your any chat. There we go. That a number of years back, I wanted to look at some comparisons of students, and in terms of how they performed in the fall term, uh, and I was doing it by actually comparing certain groups of students that looked the same, and I used a similar approach to this. That if I had a student that graduated from Citadel High School, and she, a female student, she was pursuing a Bachelor of Arts at St. Mary's. And in high school, she had had an average of 75 to 80. What I did was I went and looked at historical information from the last 5, 6 years. Did we have other female students from Citadel High School that had high school averages between 75 and 80? And I found 20 of them. I averaged how well they did in the fall term, their first year, and that was my estimate for the student that I was looking at. And this average became my benchmark. So if we introduced a program to help out first year students, I would see how does this student do compared to one that um, basically I created a profile uh, for that. But this is an alternate approach where you look at other ones that are similar and you look at that. And with a lot of property assessment, that's the way it's done. Is they look for homes that are very similar that have sold recently, and they figure this next one that's going to sell is going to sell for a price that's similar to these other ones. They may make some adjustments because that was a year ago that it sold, so now house prices have gone up by a certain percentage, and I'll make some adjustment. But um, they often do it their value estimation by just finding similar properties. That um, so uh, so when fitting these models, very often, particularly if we're using regression models, regression is popular because it can also do causal analysis at the same time, if it's possible to do that. Um, and so when we got our formula, that was like getting that $85 per square foot. That gave me an insight into how much prices go up as I build bigger homes. And but if those coefficients are correlated, if those variables are correlated, if I had a bigger house, probably have a bigger basement, probably been built on a larger piece of property. Uh, is it likely to have a garage? I don't know. That if it has a deck, might be larger. So some of those other variables might be related to each other. And to what extent can I separate the variables? And if you're finding as you add variables that all your coefficients change a lot, then you've probably got multicollinearity. If you look at your correlation and find those are quite big, probably have that. And that's what we had when we were predicting credit card balances. The rating and the income, you couldn't separate those. If you change rating, you changed, or changed income, you changed rating. So I can't look at one without looking at the other. If I'm trying to explain the coefficients, I have to be able to talk about one changing without changing the other guys. And that in our credit card question, we couldn't do. But maybe you can do it with your house prices. So multicollinearity is a problem. And related to it, we haven't really spent a lot of time on this, but because we haven't been doing time series data. If we had, we've got another problem that's sort of like multicollinearity. When I have two variables that aren't related to each other, but they're related to some third thing. And generally that, if I've got time series data, time is the factor. If you look at prices, what the price of beer is and what the price of a house is, and you looked at the correlation between the two, you're going to find it's really, really strong. So as beer prices went up, house prices went up. Does the price of beer affect the price of a house? No, but they were both affected by inflation that was happening over time. And so that when you've got time affecting house price and time affecting beer price, it may look like house prices affect beer prices or beer prices affect house prices, which isn't the case. That's Simpson's paradox type of thing, and it happens a lot with time series data. We also looked at nominal variables, yes, no type variables. We could have taken a look at ones that I have more than one value, like what program you're studying, art, science, or business. Those are nominal, and I could put that into a model. It's a little bit more involved, and I'm not going to burden you with more on that stuff. I just want to talk a little bit about what I'm supposed to do today, and I'll carry over and talk about again next week. That a few things, though, to keep in our head about aspects of the way we did modeling, because these things are going to come up later. We looked at standard error as measuring accuracy of our coefficients, like that $85 per square foot. It's not exact. It has a standard error because it's an estimate. And my estimated value of this price of the house, it's not perfect. I've just got an average, and the actual value will be higher or lower. And again, I have a standard error of a model that I can use. So I can talk about large errors and small errors and those sorts of things. And I'm not going to get into this. I'm going to skip this. So what I want to look at next is classification, because we're going to spend a lot of time on classification questions, but we're not going to get deeply into a lot of models. Well, using a lot of models, because Excel doesn't have, it's not like having regression where I can just put things in and get stuff out. Classification models generally aren't available in Excel. And they aren't available in most software unless it's really designed for doing this type of data mining. But I'd like to, it's not the formulas, just like you didn't learn formulas of regression really. It's just broader concepts. And so we've looked at one model and used it a lot to get a little bit of deeper insight. What I want to look now is the breadth of different approaches we can take, and classification is very rich. So classifying is trying to put you into a group. So not predicting a value, like what your grade point average is going to be, but are you going to come back next year? Are you going to drop out? Are you going to stay? Are you going to renew your cell phone contract? Are you going to different actions you're going to take? And I may want to look at the causal analysis. Are there things I could do to make you stay or make you leave? So it's I'm predicting a categorical variable, and that really changes things. I'm predicting, could be a binary variable, yes, no, or I could be predicting your program. Are you going to study arts, business, or science? I could predict different categories. Those are really complicated, and I, we're, I, you're going to be challenged enough thinking about simple classification, so we're going to start there. But you can, I think, if you really thought about it, you could see how some of this stuff might be extended to other types of classification. Um, so we'll stay with binary ones, yes, no type of things, and there are lots of those. You know, does a customer stay or leave? Is it valid or fraudulent? Are you going to pay off the loan? Are you going to default on the loan? That are you going to graduate or drop out? Um, Many of our classification, most of our classification problems are yes, no. So this covers a broad range of applications. So when looking at building a model, I'm going to make predictions out of the model, and I'd like to know about how accurate my predictions are. And this is the first challenging thought that you start getting into here. We're estimating an outcome, okay, but what do we need by errors? And large errors and small errors. Remember with regression, we penalized large errors much, much more than small errors by squaring the size of the error and assuming the cost is proportional to the square. So large errors were really important to us. What's a large error or a small error? Think of what the errors are. We'd predict they're going to renew their cell phone contract, and they didn't. That's an error. We predicted that a transaction was okay, but it turned out it was fraudulent. We made a mistake, maybe a costly one. We thought a borrower would default and didn't approve their loan, but it turns out that borrower was a good credit risk, went somewhere else, and the other bank was quite happy with them. And we lost a potential customer there. We predicted someone was going to graduate, and they walked away. Um, that we do lots of these. These are the mistakes we make. We picked the wrong path. So there, there isn't a size to the error. It's you're right or you're wrong. Um, it's not how big you're right or how big you're wrong. You're right or you're wrong. How often are we wrong then? That because I'm presuming we're making these decisions over and over and over again. We'll talk later about one-time decisions, which is a trickier area to get into. But so we might have different types of measures of error rates, and it may be the percentage of the time we've classified someone correctly. That we've classified this as a valid transaction when it was valid and fraudulent when it was fraudulent. But maybe we want to look at the percentage of the fraudulent transactions that we were able to identify. How often did we catch them? Or the percentage of valid transactions that we identify correctly as being valid. Or how many of, maybe we want to look at the reverse of those sorts of things. There are a lot of different rates that we may look at. It's a big area to look at, and we're going to look at it after we do classification. First, let's see how we can do the classification, and then we're going to go and look separately at that, because they're not necessarily related. The method we're using versus the error rate and how we do the evaluation. We can evaluate all kinds of different models using the same type of scheme for evaluation. So we'll do that later. But right now, I just want to look at different ways we could do it. And there are a variety of different ways. One large group of methods involves trying to not predict exactly, is it going to rain tomorrow or is it not going to rain? I think it is supposed to rain tomorrow. But very often weather forecasters, or if you go on the Weather Channel, they may say it's going to rain tomorrow, but then they tell you what's the probability of rain tomorrow. So they're hedging their bets. They're saying, we might be wrong, but we think there's a 90% chance of rain, which means it's probably going to rain. But then there are other days it says chance of showers. Today, I think it says chance of showers. and they may say a 40% chance of precipitation. So they're not quite sure. They're not making an exact classification of rain, no rain. They're giving probabilities and then leaving it to you to make the decision should you take an umbrella with you when you go out or take your chances. So it splits it into two steps. So we have a probability that we have and then a decision rule. And so we may need to build two things. One is a way of estimating the probability. How do the weather forecasters get that chance of rain? And then you need a decision rule to go with it. So, uh, and the decision rule is not just say if it's above 50%, we do this, if it's below, do that. Um, Generally, the decision rule depends upon the consequences of your mistake. Again, we can get to that later on in the course when we focus on error rates. That So if I was to estimate the chance of rain tomorrow, estimate the chance that a transaction is valid or fraudulent, that's estimating a number. I'm predicting a number. We just did that. That's called value estimation. And for value estimation, I used regression. Can we use regression to do classification, or at least the probability portion of it? It seems like a natural step from where we are. And so I've got a little data set here. It's just a contrived data set, but you could imagine, ignore the stuff that's on the right. Suppose I've got lots of employees and I have been administering when they apply for a job with me. I give them an aptitude test to test their math skills. They're just dealing with numbers, finding percentages, understanding sizes of numbers and patterns or something in numbers. And another one that's verbal skills. What are your communication skills like? Can you interpret information appropriately and so on? And you've probably, through high school, had to do these various types of standardized tests for math and for language skills. And there are lots of them out there, and they're very common. And some employers do use these two things. So let's suppose an employer, large number of employees, goes and looks and, okay, let's find 10 employees that we'd say are good employees. And let's look up their math and verbal skills. And let's find 10 that we wished we had never hired. If we had to do it again, we wouldn't have hired them. They're not great employees, but unfortunately, it's too hard to fire them or too expensive to fire them. You can fire anybody if you're willing to pay enough. And let's look at their scores. So I've got scores for the good ones, scores for the bad ones. And now I'd like to use these numbers to predict. Now, I'd like to predict the probability they're good or bad, but I don't have a probability. You're either a good employee or a bad employee. I've, I don't have ratings on them other than 0 or 1. That with if they were transactions I had in the past, they were valid or they were fraudulent, one or the other. There's no probability. They either are or they're not. I'm talking about chance of future ones maybe, but um, it's really the data I've got are zeros and ones. We've dealt with zeros and ones before, but when they were X variables, that when we used a nominal variable, are you a student or not a student, use that to predict credit card balances. I could look at the condition of a house. Is it in good condition or bad condition? Use that to predict what its selling price would look like. But now I've got the outcome being a 0 or a 1. How does that change things? So I can still build the model. I can still put that into Excel. That Excel does whatever I tell it to. So I could go up, go to data, I can go to regression, data analysis, go to regression, say that my outcome is in column B, my other variables are C and D, just like we've just done, and I get a bunch of output. And here's my output. It has an R square of 0.5288. It's not great, but that was what we got with above space by itself last time. Hey, it's not, similar. And it comes out with some numbers, some coefficients. Let me go back to my slide, it's easier to see. Here's the formula that comes out. And it's, remember, I'm predicting, is this number a 0 or is this number a 1? So it only has two values it can take on. These numbers are really tiny. That doesn't mean they're not important. Remember that the mathematical score would be 300 or 400. And the rating can only be 0 or 1. So 0.0007 times 400 would be, what, 0.28? Something like that. So that's in the same order of magnitude. Okay. Um, so don't read too much into numbers being tiny or being big, because you need to think about, is your variable tiny or big? The standard error of the model was 0.37. Now, rating is 0 or 1, so being off by 0.37 is quite a bit. But it's still hard to imagine. Let me show you some pictures that hopefully you can see this. This is the math score, and this is my rating. Is it a 0 or a 1? So if I did scatter plots, I'd find, okay, bad employees, these are the ones down here, have lower math scores than my good employees. Well, than some of them. Okay? And if I look at the verbal scores, yeah, my best, I've got a few, those with the really high verbal scores were good employees. But the rest of them, they look pretty similar. And if I put straight lines through these, they're sort of silly lines, aren't they? And, what does it mean? I want an outcome to be a 0 or a 1. I wouldn't have numbers in between here. Wouldn't have numbers down here. Okay, I can't get a negative rating. I can't get a rating that's bigger than 1. So this is a very strange model, but I can do it. Okay? And if I put it in there and we made predictions, so here's the actual rating. This one was a bad employee. This one was a good employee. And the bad ones had ratings between about minus 0.15 up to a high of 0.6. So negative here. And these ones went from about 0.3 up to 1.2 or 1.15. The numbers were higher. They're definitely not probabilities, because probabilities can only be between 0 and 1. Because I'm using a straight line, I get silly numbers that are negative, or ones over here that are bigger than 1. They're a problem. If I had a rule that said, let's draw a line here at 50%, and if you're above 50%, you're good. If you're below 50%, you're bad. Then these two guys here would be called good, but they're bad. These two guys here would be called bad, but they're good. So I'll make some mistakes both ways in classification. But the bulk of them, actually, I'd classify them correctly. So maybe it's not that bad a rule. Maybe it's not that bad a model, even though these numbers seem to be messy. I don't know. It doesn't look all that good, does it? So part of the reason is because I used a straight line. So if I want a formula, a model, and that's what I'm doing, I'm using value estimation regression type models. Before, I told you with regression, we could have curves instead of straight lines. So suppose I have a curve that never goes below 0. Lowest value is 0, and it never goes above 1. And it has this S shape. Ideally, I'd like it to go and hug the bottom here till about, what's this? This is around, sorry, I can't see it. It's too small. I think it's 380. So around 380, I'd like to go shooting up and then turn this way. And so I'd just make a quick crossover from one to the other. And the best curve might end up being of that nature, where it does a fairly quick crossover. I've just sketched an S-shaped curve. And let's do that with verbal score as well. So it jumps up. And maybe my model would work reasonably well. This one at the moment says low math scores, bad, high math scores, good. Not sure about the middle. But maybe with the verbal, it'll help me resolve the middle ones where I'm having trouble. And that two of them together will give me a better model. But this S is better than a simple straight line. At least it seems like it should. This is a very popular technique. It's called logistic regression. And this curve is called a logistic curve. It's not a standard procedure in Excel. I've used Excel to fit one, but um, it doesn't give me all sorts of diagnostics. That I think I've given you a link to an article that'll show you how to do it if you are really keen to do that. But I'm not that interested in the mechanics of doing it, and the theory behind it is really uh, it's mind-numbing. It's hard stuff. Okay, and I don't think there's any value in getting into that for you. It's scary enough just looking at the formula. This is how the model actually ends up looking. Is there's a linear portion that we use regression for, but it's of an exponent. And it appears the same way in both places here. And we work from this sort of thing to build our model. And it's a more involved process than least squares to be able to fit the coefficients for this model. But you can do it. And because there's coefficients to variables, I could start trying to interpret how important is the math score, how important is the verbal score, is it important if it's bigger or smaller or that type of thing. So I can do it. I did it with this data set, and it didn't work very well. It actually was worse than just using the simple linear regression. So here's my 50% line, and you can see with the linear regression, I got a few mistakes. But with logistic, I've got actually one more mistake. There are two guys down here. Um, and so these ones I classify correctly. Good employee classified as good, bad employee classified as bad. But these two spots are where I'm making mistakes. And so this one didn't work well. But don't believe that's the way logistic regression is in general. It's a very, very effective tool, one of the most broadly used tools. Um, and But there are other methods that you can use as well that are comparable. And so that's what I wanted to spend. Oh, I'm way over time, but give me just 2 minutes here or 3 minutes. Other approaches we could use, and I'll revisit this in the next class. But I wanted something that looked similar but was different. So here's my math score, verbal score. And in Excel, there's a way to trick Excel to plot points with different colors. And these are my satisfactory employees, my good ones. And here are my bad ones. And so as we noted before, good ones had higher math scores, higher verbal scores. Bad ones had lower scores on both. But there's some that are sort of confusing in the middle. And maybe I just put a fence up. I put a line and separate. If you're above the line, you're good. If you're below the line, you're bad. Yeah, I'm still going to make mistakes. Still get two good ones misclassified, and my bad ones, this line looks like they're just on the line. Maybe if I move that line over a bit, actually, I could probably do that, couldn't I? Hey, there, moved it over. Now all the bad ones are bad, but I've still got two good ones. So I can move that line around and find where's the best spot and make the smallest number of mistakes. This is a straight line. That's called a linear discriminant function. It discriminates between good and bad. But we can have ones that are curved. I could have one that came down like this, looped around, hooked those two good ones, and came back up this way. And so I could have a curved one. I can have them wavy. Um, there are problems. As you get more complicated ones, there are a variety of issues that come up with it. But we can create a variety of different types of functions. That one methodology is called a support vector machine. Let's see if I can actually show you what it does. Um, Whoops, no, that's not what I want. Oh, it's over here. Um, Well, I've made this a fatter line. If you could imagine me making it fatter and fatter, I'd like to know how wide can I make that line and still separate them. So I'm still separating, I've made the line wider, but I'm still separating good and bad at the moment, just as well as I did before. And the wider I can make the line, it's the bigger the gap must be between the good and the bad. And so that would be a better discriminant function. That's given a name. I'm just raising it because it's one, as you get into data mining, you'll see that people use this one. They call it a support vector machine. I thought is it something that looks like a tractor or a Zamboni machine or something? When I see a machine, I think of a machine. Um, but it comes from machine learning, from artificial intelligence, trying to teach a robot to learn. And so a robot is a machine. And this one, it support vector is a mathematical type of thing that has to do with the way this one works. But it's really just drawing a band, but more complex than that. And there's a lot of theory behind it and stuff I actually don't understand well. But that's another strategy. Other strategies might be just simple rules that if you're above 350 on both verbal and math, then good. You're a good employee. If your verbal's less than 50, then 350, then your math has to be more than 400. If you don't fit that, I'm sorry, you're no good at all. So I've got a whole bunch of rules. So I could have a rule-based system. That's another way of doing it. And we'll look at one of those later on in the course as to how do you build a rule system. Um, so all I'm trying to say at the moment is we can come up with all kinds of different types of strategies that are very different from just building one formula. We can do the formula approach, then we'll need a rule. Um, we can build a formula that gives us a fence that separates two. I can come up with rules that separate things, but it's not exactly a formula. And I can come up with other ones. And so there are different types of strategies that we can use. And I want to spend some time next time on one that is um, very different. It's called a nearest neighbor strategy. And it seems straightforward. It seems similar. You just find ones that look similar and figure that what's going to happen is what happened with those similar ones. Uh, but it raises some tricky questions about what do you mean by similar? How do you measure it? That when someone says you look like your mother, what does that mean? Is it the eyes, the nose, even that? Okay, you have the same eyes. Is that same eye color? No, it's the shape of the eyes. What do you mean by the shape of the eyes? There's a whole bunch of things. So um, similarity is a very tricky concept, but I like to get into this one and some discussion on it because similarity is used in a lot of other methods for a lot of other problems that we aren't covering in the course, but is a very, very critical issue in all these other methods. Anyway, and we might get into probability. I don't know. I'm not sure where we're going to go, how we're going to go next. Anyway, I've gone way, way, way too long. Thank you for your patience if you're still there. And you have a good weekend. And you'll see me again on Tuesday. If you got questions, send me emails. I'll try to respond to them as best I can. Still doing marking. I'll be marking again on the weekend is whenever I can get a break to get some done. But you guys take care and have a good time. And tell me, is there things, um, last class when I had yesterday, one of the students pointed out that the review of the assignment that I did helped reduce her stress. And this is a very stressful time for all of us. If there are things I can do within the course to reduce your stress, please let me know what they are, and I'll try to help you out in that regard. But I don't want to stress you out. That's not my job. Anyway, we're done for today, and I guess I better stop these recordings. You take care. Um, where am I? Back to my class. In class. There we go. Bye now. Okay.